Okay, 9.1, page 2. Okay, so the question that we want to be able to answer is this, right? How do we determine the margin of error necessary for us to be as certain as we wish to be? In other words, if I want to be 95% certain that my confidence interval contains the true population, proportion in this case, then how big does my margin of error need to be? Okay. So we're going to answer that question. First, we need to introduce a little bit of notation. So the level of confidence of a confidence interval is how certain we are that the interval contains the true population proportion. We denote the level of confidence by some percentage, and that percentage is related to a number that we're going to call alpha, and that number alpha is called the level of significance. Okay. Here's how alpha, our level of significance, is related to our level of confidence. For a 95% level of confidence, alpha would be 0.05. The way that you get that number, the way that you get alpha based on your level of confidence is you take your level of confidence and subtract it from 100%. Okay, so 100% minus 95% is 5%. And then you change that to a decimal, right? 5% as a decimal is 0.05. Okay, so what I want you to do is pause the video, see if you can figure out what alpha would be for a 97% level of confidence, right? So pause the video, give it a try. Okay, I'm going to answer the question now. For a 97% level of confidence, to find alpha, we would say, all right, 100% minus 97% is 3%, and 3% as a decimal is 0.03. So alpha would be 0.03. Okay, so that's the level of significance, right? Alpha is the level of significance. Now the next thing we need to talk about is this notation for z-scores. When you have a subscript on your z-score, so when you have z sub k, this denotes the z-score whose area to the right is k. Okay? We can use StatCrunch to find those values, and we'll practice doing this in a second. Okay? But for a 1 minus alpha times 100% confidence interval, z sub alpha over 2 is called the critical value. So to find the critical value, z sub alpha over 2, we use the normal calculator with mean 0 and standard deviation 1. We call this the standard normal calculator. You might have some problems in the textbook that ask you to compute something involving the standard normal calculator. When they say standard normal, they're talking about the normal calculator with mean 0 and standard deviation 1. Okay, so to find the critical value z sub alpha over 2, we use the normal calculator, the standard normal calculator, and we compute the value of z so that the probability x is greater than z equals alpha over 2. So the subscript here gives us the area we're looking for. All right, let me give you a couple examples of this. I know that your head's probably swimming a little bit. You're like, I have no idea what he's talking about. If we look at a couple examples, I think it'll be a little more clear. Okay. So example 2 here says, find the critical value for a confidence interval with the following levels of confidence. Okay. So the critical value for a 95% confidence level. The first thing we need to do is figure out what alpha is. Okay, so for a 95% level of confidence, alpha would be 0.05. Okay, because 100% minus 95% is 5%, and 5% as a decimal would be 0.05. Okay, so that's alpha. Our critical value is z sub alpha over 2. Okay, so we're looking for z sub alpha over 2. That would be z sub 0.05 divided by 2. 0.05 divided by 2 is 0.025. So we're looking for z sub 0.025. In order to get that value, we go to StatCrunch, we go to the normal calculator, we leave the mean on 0 and the standard deviation on 1, and we change the area to 0.025. Okay, so let's go to StatCrunch to calculate that value. Okay, so we're going to go to Stat, Calculators, Normal, leave the mean at 0, leave the standard deviation at 1. Critical values are always areas to the right, so we want to shade in the stuff going to the right. And then we want the area to be that subscript that we just calculated when we were working it out on the page. We want the area to be 0.025. Okay, and then we're going to hit compute, and our answer is going to show up here in this box. Okay, so there it is. We usually round critical values to 2 decimal places. So we would say this one is about 1.96. Okay. Okay, so this is about 1.96. Okay, that's the critical value for a 95% level of confidence. Some of these values come up over and over and over again, and so you'll get to the point where you have them memorized, right? 95 is one of those. 99 is another one, but you don't have to memorize them. You can use StatCrunch to get them. Okay, so part B says we want to find the critical value for a confidence interval with a 99% level of confidence. Well, if our level of confidence is 99%, then alpha should be 0.01. Okay, 100% minus 99% is 1%. 1% as a decimal is 0.01. Okay, our critical value is going to be z sub alpha over 2. That would be z sub 0.01 divided by 2. That's z sub 0.005. So again, we're going to go to StatCrunch, and we're going to fill in area of 0.005, right, in the normal calculator. So let's do that. Okay, so we go to Stat, Calculators, Normal. We're going to leave the mean at 0, the standard deviation at 1. We want an area to the right. We want that area to be 0.005. Okay, then you hit compute, and there is the critical value. To 2 decimal places, we would say 2.58. So it's about 2.58. Okay, 2.58. Okay, so now that we have that notation in hand, we can answer the question, right? The question we wanted to answer was, how do we determine the margin of error necessary for us to be as certain as we wish to be, right? Well, so here's the answer, right? Here's the formula that will do the trick. Okay, so suppose that a simple random sample of size n is taken from a population. 1 minus alpha times 100% confidence interval for p is this interval right here, p hat plus or minus critical value times standard deviation. And just as a reminder, right, sigma sub p hat is going to be the square root of p hat times q hat over n. Q hat is just 1 minus p hat. Right, so this is all building on itself, right? But these things should all look somewhat familiar because of the work we've done in the past. Okay. One thing to warn you of, your book is sometimes, on some of the problems, your book might ask you to check conditions to make sure that p hat is normally distributed. This is what it's asking you to check for. Okay, it's asking you to check these two things, right? So you need to check to make sure that n times p hat times q hat is bigger than or equal to 10. And you need to check that little n is less than or equal to 0.05 times capital N. That one is hard to test sometimes because you don't always know what capital N is. And the other thing is that it almost never fails, right? If anything fails, it's usually this other condition. But if your book asks you to check conditions, that's what it's asking you to do, okay? Another thing that I'll say is that I'm not getting into a ton of detail right now about how we arrived at this formula. You have the tools that you need in order to understand that. So if you're interested in understanding how we get this formula, take a look at your textbook. Page 425 of your textbook contains the derivation of this formula. So if you want to know why this is the interval that does the trick, then you can take a look at that page in your textbook. But I'm just going to show you how we apply this formula, okay? How we apply and how we interpret the formula as well. Okay, so let's look at an example, and I'll start a new video.